Okay, welcome to chapter 6. In this chapter, we are leaving calculus behind and moving into the world of vectors. Now, for those of you who have taken some physics in the past, this is kind of a double-edged sword. You've already seen vectors, and so this tends to go one of two ways for students. Some students, this provides a great background knowledge, and it helps them understand the material in the math sense of vectors really well. Other students have trouble moving on from their understanding of physics vectors into the world of math vectors. So it's the same sort of concept, but from a different lens. So we do the math steps in a different way, and you need to be prepared for that change. All right, so in the first lesson, I am assuming that you've never seen vectors before, and some of the terminology might change in the math world. So I'm going to go through a lot of vocabulary today. So the first thing that I want to do is talk about the difference between a scalar and a vector. A scalar is usually what we've been dealing with in math so far in high school. It's a quantity without direction. A vector, in comparison, is a quantity, and so that implies that it does have an amount, and we call that a magnitude. So it's a quantity with magnitude. That's like the size. But it also has a direction. Over on the scalar side, a scalar has a size or a magnitude, but we just think of that as the quantity, the amount. Okay, so some examples. In the scalar world, we might talk about speed. Like maybe the speed is 45 kilometers per hour. In the vector world, we would talk about velocity. And the velocity is going to have a direction. So sometimes the direction is based on our map, and so we could say like it's 45 kilometers north or something like that. Or maybe it's, we could also say it's 45 kilometers and maybe this time it's south but 40 degrees to the east from south. And I know in physics class you guys write this the other way around. But in our textbook, you're going to see this format here. All right, another example of a scalar would be a distance. So I move a distance of 10 meters. In the vector world, we talk about displacement. And with displacement, we need to know the direction as well. So I might say I moved 10 meters to the right. Or again, this direction could be in terms of north, south, east, west, something like that. And vice versa with the velocity. It could be to the right or up and down. Well, there's lots of different ways to talk about direction. Some examples of scalars that don't transfer over to the vector world are things like temperature. We typically wouldn't make this a vector because it only has the two, the positive and the negative. Typically we just leave temperature. It doesn't have a lot of use over in the vector world. And same with like maybe the volume of a shape. We would say that the volume is maybe 54 centimeters cubed or something like that. These typically stay over here in the scalar world. A vector quantity that you might not be aware of yet is force. So we could talk about the force of 15 newtons, so this might not be a unit that you're familiar with, and then we would give a direction like 30 degrees from the horizontal. So here are just some ways that we talk about direction. Another way, I wanted to go back to velocity, another way is just bearing. And so I could say that the velocity is 45 kilometers per hour with a bearing of 170 degrees or something like that. And we're going to talk about what that means in some of our examples in future lessons. So lots of different ways for me to talk about direction there. All right, notation. So this is where I'm going to be looking for, do you understand whether you're looking at a scalar or if you're looking at a vector? So notation for scalar quantities are just variables like a, b, or we love to use x in math. For vectors, you're going to see the notation with our variable. Usually we use a lot of v's for vectors. But there's this added addition of an arrow on top. So sometimes you'll see people write it with just the top part of the arrow, or sometimes people will write it with the top and the bottom, and either one is fine. I tend to do this first one because it's just easy. I'm a little bit lazier like that. So sometimes we call a vector v, and sometimes we name it by its endpoints. And so I would typically name those endpoints with capital letters, and I would say that the vector goes from A to B. And it is significant where the order that I put these letters in, and we're going to get into that in future lessons. All right, so the arrow on top signifies that these guys have a magnitude and a direction, whereas these guys only have a magnitude, just an amount. If I wanted to look at just the magnitude of these vector quantities, I can do that by we put these absolute value bars, and now we're going to call them magnitude bars. And when I use this notation, I am looking at the magnitude only, and I can do the same with the other version of a vector. So both of these I'm looking at magnitude only. All right, so what might that look like in a diagram? Well, when I draw a vector in a diagram, I have to indicate its direction. So I'm going to grab my line tool. So when I draw the vector, I have to make it really clear which direction I'm going in. So I have to draw an arrow on one end. Now, to talk about the vector, we're going to talk about this arrow end as the head of the vector and the other end as the tail. And again, either I would call this vector v, or maybe I'd label the ends of the vector as a and b. And that's matching my notation up here. In this picture here, what I have is that vector v is the same as vector ab. When I draw my vector, I indicate the magnitude by changing the length of my drawing. And I'm going to change the angle when I have two vectors or other objects in my drawing. I'm going to make sure that the angle between the two matches the situation. So the angle will indicate my direction. Sometimes they'll give me that direction in terms of northeast, southwest. So here in this picture, I've drawn it heading to the northeast. But sometimes they won't. They'll just say vector v is 45 degrees from vector u. And then I could draw it in multiple ways. So I'm just going to, this is just a rough example. If u and v were 45 degrees apart, I could draw them like this. Or somebody else might draw them like this, and they could change the order. They haven't really told me a lot of information about direction, just that as I spin them, I get a 45-degree angle between them. So be careful with that. When I'm not given like northeast, southwest, I don't actually know which way they're pointing. I just know their relationship between the two. All right, so heading back over to the diagram for a scalar, when this is like stuff that we've done throughout high school and even elementary school. So perhaps my scalar is part of a triangle, right? Like maybe I've got like my scalar A, B that I have above. Maybe this is another B, maybe this is like an isosceles triangle, something like that. So these would be scalars. This is one example. We've seen lots of different examples. Any kind of diagram that you've ever drawn in math before is probably involved scalar measurements. All right, so those are some of the basic building blocks for vocabulary. We're going to talk about different types of vectors next. All right, so types of vectors. One term that we're going to talk about are equal vectors. Now, equal vectors have the same magnitude, so that means like the same length, and the same direction, so the same angle, but not necessarily the same position, which means they might not be on top of each other. So sometimes we call these equal vectors and sometimes equivalent vectors, same idea. In my picture here, if I had a vector y here and I wanted to draw an equal vector, I could draw it here and say this is vector w, and now w and y are equivalent or equal vectors. In a math statement, when they're equal vectors, even though the position is not the same, I can write that w is equal to y. All right, the next one we've got is coincident vectors. Now, coincident vectors have the same magnitude. The same direction and the same position. Sorry guys, I'm not sure what's going on here. Okay, so that means that they have the same length, the same angle, and they're actually on top of each other. So this time, if I wanted to draw a vector that was coincident with y, it would have to have the same length, and it would also have to be pointing to the right, same direction, but it would have to be right on top. So maybe I'll call this vector k. And here I can say that, sorry, I'm just making sure I'm not repeating any letters in my diagram. So now I can say that vector y and vector k are coincident. Now, if two vectors are coincident, they're also equal. So I can use this notation again and say that y equals k. But this only tells me that they're equal. To say that they're coincident, I would have to add a note beside that. Like I would have to just put it in words and say that they are coincident. All right, opposite vectors. Opposite vectors have the same magnitude, but they point in opposite directions, so directly opposite. So in my diagram, I actually already have a picture of two opposite vectors. Vector AB, I can see that that's the same as vector D to C, but in the opposite direction. I know it's got the same angle because when I count over, I get 1, 2, 3, 4 squares over and 1, 2, 3 squares up. And this one has the same 1, 2, 3 squares, or sorry, 4 squares over and 1, 2, 3 squares up. So I know it's for sure on the same angle. So I've got the same direction, it's just that the arrow's on the opposite end. So this one's pointing up and this one's pointing down. So I would say that AB and D to C are opposite vectors. Notice that when I name my vectors, the end of the vector where the head is always comes second, and the head of the arrow in the notation is above that letter. So when I say A to B, the arrow's on B. In the notation A to B, the arrow is above the B. And I would never write it backwards. This is not a thing that we do, writing the arrow backwards. I just have to put the head second and the tail first. All right, now if I wanted to write these guys in a mathematical statement, I can do that. I can say that AB is almost equal to DC. I would just have to switch the direction, and I can do that by putting a little negative sign in front of it. So if I were to flip the direction of DC, I would end up with an equal vector to AB. All right, a unit vector has a magnitude of 1. Right? The word unit typically means 1. And so I can draw a picture of a unit vector. Usually when we talk about unit vectors, the accepted notation is to call it U. And so in my picture, I'm going to say that the scale of this grid is 1 by 1 squares, and so I can draw a unit vector like this. Now somebody else might have drawn the example with the unit vector like this. That would be acceptable as well. These are obviously two different unit vectors, so I could call this like unit vector 1 and unit vector 2, and those are both examples of unit vectors. So in my graph, I've got the U1 or the U2. And notice that in both of these cases, that vector U's magnitude, so I'm adding the magnitude bars, is equal to 1. All right, the last definition, oh, sorry, two more. Collinear vectors. Collinear vectors are parallel. This means that they have the same or the opposite direction. But they could have different magnitudes, so the lengths can vary here. Collinear vectors can also be written as scalar multiples of each other. So let's see if we can find some collinear vectors in our picture here. So as soon as I have equal vectors, they are definitely collinear. And obviously then coincident vectors are also collinear because they're parallel. Opposite vectors, again, also parallel. So they're going to also be collinear vectors. So all these first three definitions are also collinear vectors, but being more specific, we would use one of these first three definitions. In my picture, I also noticed that going from E to C is collinear or parallel with going from A to B. So I can write them together. So A, B, and EC are collinear because they're parallel. And I can write them as multiples of each other. So I can say that EC is equal to 3 ABs, but I need to switch the direction, right? So going from E to C is the same as 3 ABs. So if I think about just matching up the line length, let me throw an end on that. So A to B was this vector here, and I can grab that vector and I can see that it's going to be the same. It lines up 1, 2, 3 times. So that's where I came up with the 3, but it points in the opposite direction. So I also need to flip the direction, and I can do that by putting a negative in front of EC or in front of the 3AB. Either way is fine. So this is what we say, I'm writing it as a scalar multiple of each other. So I'm putting a multiplier in to change the length of AB. And there were other examples in our diagram. For instance, even going from C to E is the same as going from C to D 3 times. So now I'm switching the direction and I'm saying starting at C, heading to E, that's the same as C to D 3 times. I'm just going to come up and show that. So here's C to E, and it's the same as 3 C to Ds. So there's a C to D, and if I do that 3 times, I'm going to get 2 equal vectors. The arrows are pointing in the same direction. And this is going to happen whenever I have parallel vectors. I will be able to write them as a scalar multiple of each other. All right, the last one we need to talk about is the 0 vector. A 0 vector has a magnitude of 0 and no defined direction. Because it has no magnitude, it doesn't really point in any one direction. When we write this, we write 0 with the arrow on the top of it. And this is, you can kind of think about it on the graph as like a point. So I could draw the 0 vector we typically wouldn't draw it, but it would just be a point on the graph because it has no length. And so there I can't really put an arrow on the end of that, and that's why there's no defined direction for that guy. If I wanted to talk about the magnitude of the 0 vector, it's equal to the scalar 0. So these are different things. This is a vector, a 0 vector, and this is a scalar 0. So watch out for that. All right, in this question here, we're given a parallelogram. We're going, and we want to determine if each statement here is true or false. So I'm going to draw on this diagram multiple times and erase it as I go. So the first question is asking about going from W to Z. So the arrowhead is above the Z. So I'm starting at W for my tail, and I'm drawing the head at Z. And it's saying that WZ is equal to X to Y. And we want to know, is that a true or a false statement? And this one here is a true statement. It's true because the vectors have equal magnitude and they have equal direction. They don't have the same position, and that's okay though. When I use this symbol, I am just talking about magnitude and direction. All right, the next one is asking about the magnitude of W to A, so the length only is all I'm considering here, going from W to A, and then it's also asking me about the magnitude starting from Y and going to A. So here all I care about are the lengths because of the magnitude bar. And I do have that these two lengths are equal to each other, even though I can't draw a straight line very well, and this is a true statement. Oh, I went down instead of across. Okay, so we'll go to B now. Part B says going from W to X, so again, the arrow is at the X, is equal to going from Y to the Z, and again, the arrow is at the Z, the head is at the Z. We call Y the tail. And so this statement here is saying that they're equal. Now remember, for two vectors to be equal, they have to have the same magnitude. These guys do. But they also have to have the same direction, which these guys do not. So this is a false statement. I could change it into a true statement just by changing the direction on one of them, which I can do with a negative sign. I can either put the negative on the WX or on the YZ, and it would make it now a true statement. So these are opposite vectors, not equal. All right, in part D here, we're looking for W to A. So again, tail at W, head at A. And it's asking, is that equal to starting at Y and ending at A? And so again, for equal vectors, I need to have equal magnitude, which I have here, and I have to have equal direction, which I do not have here. These guys are pointing in the opposite direction. So again, this is false. And I can correct this statement by either making the first or the second vector by switching its direction. I put a negative in front to indicate that. Another way you could correct this statement instead is by switching the order of the letters so that the arrow ends up on the W. So if I wanted to draw this vector here, I would say this is A to W. And then I could write that A to W is equal to Y to A. These are equal vectors. All right, our last example, we're going from W to X. So the head is at X, and then we're saying that that's the same or equal to starting at X and going to W. And this is not true. These vectors have equal magnitude and equal position, but they do not have equal direction. So they are not equal vectors. I need to have equal magnitude and equal direction. So this guy is also false. And again, I can correct it in a variety of ways by putting a negative in front of one of my vectors. Is going to be the quickest way to correct that. All right, so today what we've been looking at are called geometric vectors, and that's normally what people focus on in physics class. And that means that these vectors are just kind of floating around freely in space and not glued to a coordinate axis. Sometimes, though, we're going to move into some lessons that focus on algebraic vectors, and I think you're going to find that the math simplifies a little bit more. And what's happening there is we're placing them on a coordinate plane, so like an XY plane, and they'll be like coordinates for the points. So we're thinking about putting them on a plane like this, or in some sections we're going to move into 3 space. All right, so that's it for today. Good luck with that homework.